Yeah. So I came from Amsterdam. And since the party is near, we're expecting a party in an hour, so I bring you some legal stuff. Oh, some legal stuff. Legal stuff for characters. Who can guess? Legal stuff for characters. JLSL. JLSL is an OpenGL shading language. It's basically the way to interact with GPU, with graphics accelerator, and now it's legal on the web via WebGL. And we'll talk about HTML-GL library, which allows to render HTML and CSS content via WebGL to boost performance a bit. In Amsterdam, I work in a company called UPC, or it's maybe famous as UPC in Germany, in Amsterdam, Zigo. And we do set-top boxes for millions of our users. We deliver a set-top boxes with JavaScript UI, with JavaScript operation system. And basically, performance is quite extremely important there. So everybody wants to have a snappy UI on a set-top box when watching movies, etc. But device is pretty weak. I mean, it's compared to iPhone. And if you say, OK, I don't care about this embedded JavaScript, about your set-top boxes, why should I take care about performance? Because there are a whole bunch of mobile phones, and users on mobiles want to have this snappy 60 FPS performance, 60 FPS experience as well. Also, performance is not the only thing, because performance optimization is not the thing which only makes your application faster, but also it allows to make things which you're not able to do before. As illustration shows, the slow turtle can jump, but rabbit, having a bit more speed, can. So more speed, more possibilities. Basically, you can add more effects. OK. The problem of HTML and DOM is that DOM is quite a complex model. It's quite slow. I mean, have you ever tried to inspect DOM elements? There are hundreds of properties. A lot of events being fired on every change, like you touch one DOM element in document, poof, you have ripple of events, chain effect, and that's it. You got a lot of calculation to do just for one change. So DOM is slow. Let's consider how image is going to be displayed in DOM and in Canvas. So for DOM, you need to create image tag, to load file, to open image tag to DOM, to calculate styles, which styles to apply, then calculate position based on the styles, then display image. Okay, not that much, but for Canvas it's much less. It's load an image, display an image, and it's easy. So even GPU DOM is slow because it changes the only how image is being displayed. So DOM still stays. This complex model still stays. Yes, one more problem. DOM is hardly predictable. Browsers are quite smart. They are too smart sometimes. On the image, on the diagram, there is the same component being rendered in DOM and Canvas with the engine which allows to render, which allows to switch from DOM to Canvas. And what we see is that in DOM, it's hardly predictable. You can hardly predict when browser re-renders. In Canvas, you say, render, please. You can say it once per frame or once per 2 frames, etc. I mean, you can tune FPS as you wish. And you really know when you re-render, when you change content. DOM, browser do everything for you, so basically it's hardly predictable. So HTML-GL, the library which we are talking about now, doesn't use DOM, but only when it's animating. When it doesn't, it's still inspectable, still editable via inspector, via DevTools. So it's quite easy to develop because you still have tree and inspector. So also, yeah, probably you can recognize this one is a GPU. Everybody in this room, I suppose many people in this room already been a bit annoyed by GPU render via GPU. But yeah, still, we should consider and we should understand that GPU is quite powerful unit to display graphics. And Yeah, this one is kind of professional GPU from some Radin video chip with bunch of memory to GPUs to graphics processors and so on. But something similar you have in any device you can get, almost. Any phone, any PC, any Mac have GPU inside. And even in iPhone, GPU is as powerful as PCs you played Counter-Strike 5 or 10 years ago. I mean, iPhone is pretty powerful in terms of GPU. Everybody watched this movie, probably. Oh, who watched this movie? Should we watch it? 2 people, 3 people? Who? OK, so should we watch it or not? Yes. OK. So this movie shows the difference between GPU and CPU.
Building an application and keeping it secure is a lot of work.
It's not a sponsor.
One unchecked step could leave the whole thing exploitable by hackers. And who wants to figure this out after it's released? Wouldn't it be nice to discover and fix vulnerabilities earlier in the process?
Button for that one.
Say hello to Checkmarks. Checkmarks scans uncompiled software source code, quickly identifies security vulnerabilities
Is there anybody from Relic?
Issues, and shows you where and how to fix them. By scanning uncompiled code, complex builds are not necessary for Checkmarks to do its job. You can literally throw code at it and get great results right out of the box. So check out Checkmarks today.
Thank you. Leonardo.
So Mythbusters will show us the difference between rendering via CPU and GPU.
CPU might do it as a series of discrete actions performed sequentially, one after the other. In 3,
this robot
2,
emulates
1.
CPU. CPU puts every pixel step by step. It calculates which pixel it should be, what's the color, where it should put it. So a lot of considerations on every step.
Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on
this one is GPU.
2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10, 9,
8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over.
Thank you guys. So the difference is pretty big. If you simplify, CPU is a hard working kit, which is put in every line by line using a pencil, and GPU is another kind of kit, using stamps. And if you use stamps, you can get it more effective and much faster to do that. So modern GPUs can process millions and millions textured surfaces in a second. Just for us, for web developers, it means millions of HTML elements, like textured surfaces, we can compare. Yes? Cool. Why so many? Because for some things, it's still not enough of details. 3D needs a lot, but we can use this in 2D. And if we have a look at the power we have in our PCs and our Macs, it's pretty amazing. So let's try to see what GPU do in modern games, because WebGL and OpenGL is basically technologies are being used in modern games. And the same technology you can use to render HTML and CSS. The hand of this guy consists of about 50,000 of textured surfaces. It means you can run 60,000 of HTML elements animated with dynamic lighting, with all special effects. But the question, the same hardware, the same stuff, they can do that, run all this FX, bunch of surfaces, bunch of images at 60 FPS. Why simple slider janks? And yeah, simple slider janks. No, because GPU is not involved sometimes, and DOM is quite complex. So changing one thing, you are making a massive chain effects. And still, we can move away from DOM and use OpenGL by using a wrapper on OpenGL, which is called WebGL. Many of you know about that. And now we can check how performant WebGL is comparing to OpenGL. So would we be impressed by the performance? So let's release bunnies. This one is a very simple benchmark. And now we have two bunnies, like every bunny, to make it clear, every bunny could be compared to HTML node, to HTML element. So now we have two bunnies and running at 60 FPS. It's cool, two HTML elements, and we add in them. Oh, 5,000 bunnies, 10,000 bunnies, 50,000 bunnies, 30,000 bunnies, still 60 FPS, 50,000 bunnies, 60. Okay, guys, FPS dropped a bit. No, still 60. I mean, already 80,000 bunnies. So could you imagine, you can animate 80,000 of HTML elements at the same time with WebGL. I suppose nobody even can imagine to do that with DOM. But yeah, now it's possible. A lot of bunnies. Okay. Yeah, so why don't we use WebGL for web content? It's a bit tricky, basically. So if we compare HTML we are common to with WebGL, we'll see that it's not that easy. So displaying one image with WebGL, and basically it's not even plain WebGL. It's a 3JS. If you know that, it's an engine, like a high-order engine, which allows to make everything in easy, simple way. So yeah, with plain WebGL, it will take 5 times more. So, and we, as lazy HTML developers, we can do that. And basically, it's sad. But here, HTML.jl changed the game. It's pretty simple. You can just wrap your content with HTML.jl tag, and your content has been rendered in WebGL. Awesome. Pretty simple. And it's really easy to use. You can use it as jQuery plugin if you want, of course, to mix all these things, WebGL and jQuery. And yeah. Also, you just animate. It's as simple DOM element. You can put some listeners or etc. So how it works? When browser meets HTML.jl element, it rasterizes it to texture, basically to a canvas element, and then can put it to a full screen WebGL surface. So it's being displayed, and if something, do I have a laser here? Yes, green one. And yeah, so if something changes, there are 2 ways to go. The first one is if content changes. I mean, if you change the font to bold or color, so you need to rasterize once more and display it once more. But if element was transformed, translated, rotated, opacity was changed, so it's very cheap operations you can do on GPU. So these operations, transformations, animations, being made with GPU on this WebGL representation of this WebGL sprite, basically it's extremely cheap and extremely fast. So HTML.jl relies on DOM mutation observers just to react on document change, on element change. It relies on HTML to canvas. It relies on Pixie.js as a renderer. The weak thing here is the HTML to canvas. It's basically a bottleneck, because every rasterization takes about 150 milliseconds. So it's quite expensive operation. And if you ever met the need to rasterize content, and you tried HTML to canvas, and you found, hey, guys, there should be a better way to rasterize something to in canvas, please share the word on the intent to make rasterization API, which will allow document rasterize node, then get canvas. And we already have a polyfill as HTML to canvas, but in browser it could be much more performant and less buggy. There is an article on my blog on that, and there is basically a draft on proposition on spec. So if you're interested in rasterization API somehow, please help me to spread the word on that. OK, let's come to some live coding, which always sucks. Yeah. Let's see. Simple demo. Have is it fine? Yeah, it should be. So we have HTML/GL element. Nice. But the issue is that this page doesn't include HTML/GL library, but it's still valid HTML. It's basically a custom tag. It could mean nothing, or it could mean please render to WebGL. So in this case, it means nothing. And pushing the animate button, we see that at the edge point, browser make a decision to rasterize text once more. So let's repeat. Look at the edge point. We see the image is a bit blurry, and then browser thinks, OK, let's rasterize. That's basically what I said, that browser is worse predictable. It could mean a jank on a mobile phone, because you need to rasterize the font, it's vector, you need to rasterize it, it takes some calculation power. So WebGL allows to avoid that. Let's move to the same demo, but basically it's the same, absolutely the same HTML, but HTML/GL library is included. So yeah, if you press the button, the same happens. Absolutely the same JavaScript code animates, but basically we control rasterization. We can rasterize manually, but we may postpone it for later. But yeah, I mean, we control rasterization, and we use WebGL to animate that. OK, let's try to change content on layer. So thanks to mutation observers, all changes you are making on node, so you're changing inner HTML or whatever, they're being cached by HTML/GL, and node is being re-rendered. So you don't care about that. So let's proceed to the next example, which is more complex. And basically, this is one of prototypes we did in Liberty Global, some list of movies, and it slides, basically. What we see here, that nodes are still on the same place. So when we animate only WebGL representation. But actual nodes are state place, and still everything is expectable, and we can change the content. So WebGL, but it re-renders. Also, what's nice to mention in this demo, so even we click on WebGL representation, not on the node, you can still use the events in the same way you use them in HTML. You basically add on click or add in listener. Everything is the same. You still use your DOM elements as a facades to HTML/GL representations. And this one and previous was possible to implement in DOM or HTML/GL. The next one is only HTML/GL thing. You can do this with DOM. So we have some filters on that. Yes, it's a kind of displacement. We can add more. And it's still, you know, what is nice? It's still HTML content. You still can inspect that. It's too much. But you can apply all kinds of shaders you can expect from OpenGL. Just a bit more. Just let that screen. Nobody would be impressed by blur nowadays, but okay, we have blur, we have any kind of modifications, we have twist. Okay, cool X twist. It's still HTML content, and we still can inspect that, and basically, yes, we still can change a content and talk to our content as we comment to. Oh, the next demo is quite epic. It could be useful for PhoneGap users. And it basically shows how you can work with effects, how API is built. And yeah, it's a nice effect, like ripples. So it's a simple page you can build with float or display inline or whatever, just some icons. You have a ripple effect on that, and effect is being applied with this effects attribute. Let's add some more. Let's add some noise. Poof, we have some noise. Let's move it to mobile. I suppose it's going to be cooler being a mobile. Let's add invert. Poof, we inverted the colors. Let's add some contrast. Poof. I mean, it doesn't look like our initial HTML. It basically was modified by using shaders. And, yeah, my favorite one, twist, of course. So, yeah, that's still HTML, guys. It's still understand? Yes. You don't need to study new conceptions. Everything is just HTML, CSS, and you work with them with your command to. So you can add effect as a plugin, and you can add your one. Have you ever heard? No, I don't think you ever heard. There is a shader toy. Shader toy is a website where you can find a whole bunch of shaders, like predefined shaders, any kind of effects, effects of sky, sun, I don't know, heaven, hell, or whatever. I mean, just any kinds of effects you can imagine. You can modify your content absolutely in any way you can imagine to. Basically, all power of GPU, which is being used in modern games, is to your service, to modify your web content. Yeah, of course, it's open source. And the nice thing, it's really framework agnostic. So you just put your HTML GL tag anywhere you want, any framework. But there are some bindings for Ember. And yeah, there is a link, and there is a binding for WebGL. So yeah, you may use it together with React as a HTML GL tag, or use a WebGL bindings like a React component. All this stuff was consequence of my work in Liberty Global on the set-top boxes, on the UIs for them, and on mastering a Challenge Native workshop. And Challenge Native is a workshop on making performant web applications which are able to challenge native ones. So if you're interested in that, just go to this website. You can find some information there. This is a second block of advertisement. So thank you very much. If you have any questions, you may reach me here or via my Twitter or email there. Thank you.